Patent 512340, Coil for Electromagnets, awarded on January 9, 1894, also known as the bifilar coil, Tesla coil, or supercoil, since it is the basis of several other patents, including art of transmitting electrical energy through the natural medium, method of signaling, system of transmission of electrical energy, and apparatus of transmitting energy through the natural medium. It deserves a closer look. Normal coils are wound with a single filament. As current moves through them, the magnetic field around the wire interacts with the next loop and gives rise to countercurrents which degrade the performance of the coil. Given a coil of 1000 turns which shows 100 volts potential between its ends, there will be a 1/10 volt difference between 2 points on adjacent turns. This animation shows how the current flows through the Tesla coil. Two filaments are wound in parallel and connected in series. Current flows through the first coil to its end, then it goes along a parallel path to exit at the expected point. His aim is to do away with self-inductance and to avoid using expensive capacitors. In this coil, under the same conditions as the normal coil from before, the voltage potential between adjacent coils is now 50 volts. He explains that the energy stored in this type of coil can now be up to 250,000 times greater than the normal coil. To test this theory, I built a small coil following his specifications with an added twist. I used two different sizes of magnet wire. I used a function generator and an oscilloscope in the lab to test it. In the generator, I have stored 3 square wave signals at 2 volts peak to peak with a DC offset of 1 volt to maintain reference at 0 volts in a 20% duty cycle, which is the lowest the device can provide. The signals are set at 215.7 kHz, 107.8 kHz, and 72.1 kHz. First, I use a 2 kHz signal to find the resonant frequency of the coil. It can be clearly seen and measured in the scope. It is about 216 kHz. Then, to show you how the coil responds to a resonant frequency, I send it a 72 kHz pulse. You can see it produces a sine wave of 3.4 volts. Next, the 107 kHz pulse produces a sine wave at 5.4 volts. And finally, the 215 kHz signal produces a 6.4 volt sine wave. To keep distortion of the input signal to a minimum, so you can see the relationship between input and output, I had one of the input leads disconnected and now connected back. With both wires connected and the input pulse at 215.6 kHz, I now show a 31 volt sine wave. At 107 kHz, a 26 volt sine wave. And at 72 kHz, a 17.8 volt sine wave. The coil always resonates at the same frequency of 216 kHz, regardless of the input. As a reference, at 100 Hz, we can see that only a short pulse of 2.8 volts peak to peak is generated in the coil. Now I will show you the effects of resonance. I am using a 72 kHz signal, which you can see from the scope corresponds to the third harmonic. I will sweep the generator's frequency to show you what happens to the coil as I feed it a signal that goes in and out of resonance. You can see that the sine wave rises and falls as I float past the resonant frequency. Next, I introduce a 6 MHz 10 volt peak to peak sine wave. You can see that the 6 MHz neatly rides the coil's resonant signal. The new sine wave is fed in through a single loop of magnet wire, just like the pulse signal. Again at 8 MHz. And at 12 MHz. I wonder what a coil made of iron wire will do. Thanks for watching.